So we have two different types of compounds. We have molecular compounds and we have ionic compounds. We need to spend some time learning how to write good formulas for these compounds and naming them, okay? It's called nomenclature. So we're going to start with the world of ionic compounds and learn the system for writing good formulas and writing good names. It's the more challenging of the two systems. There's a completely different system for molecular formulas that we'll look at in our next lecture, and it's easier. Its biggest challenge is making sure you follow the right rules because you're so used to these after you learn them first. So you just have to keep them straight. Okay, so what is an ionic compound? It's a compound consisting of ions, cations and anions. We know that the cations are positively charged ions, right? So our cations are positively charged, our anions are negatively charged. We know that opposites attract and formulas are going to come together. I mean, those ions are going to come together to make our formulas, okay? Now, and we're going to see why this is as we proceed through our world of chemistry, but metals bond with nonmetals most typically by these as ionic compounds. Metals love to turn into cations, nonmetals love to turn into anions, and as soon as you have opposite charges, they're going to attract, okay? But it doesn't have to be a metal and a nonmetal. We could also incorporate in any of those polyatomic ions that you had to commit to memory. And if you have not committed those to memory, you've got to get going on that. You've got a lot of them to learn, so make sure you do so. So here are some examples. Some of them have polyatomic ions in them and some of them don't. The first one we see is metals and nonmetal. Magnesium is a metal, chlorine is a nonmetal. Now, why that subscript 2? We'll learn why that subscript 2 is there. Right now, it's not because chlorine is always diatomic, because it's in a compound, not elemental. The second example, I have a metal with a polyatomic ion, phosphate. If I'm not familiar with my polyatomic ions, I might think I've got a metal and two different nonmetal anions, and that's not the case. In the third example, I have a polyatomic cation. I'm familiar with ammonium, NH4+. There is the cation hooked together with a nonmetal anion. So those are some examples of ionic compounds. Now, not in chemistry do we use this word very much, but you need to be familiar with it. The word mineral is an ionic compound that occurs in nature, okay? So if you can go and dig it out of the ground, we apply the word mineral to it. So sodium chloride is table salt. You can dig sodium chloride out of the ground as sodium chloride. You can go out to Utah and they have big mines just full of sodium chloride. Now they usually have special names when they're minerals. They don't call it sodium chloride. We call it sodium chloride as chemists, but in the mineral world they call it halite. That's the name of sodium chloride as a mineral when you dig it out of the ground. So not every ionic compound out there can be found in nature, but the ones that are found in nature are minerals. So sometimes they talk about taking vitamin supplements, or it'll say vitamins and minerals. The minerals are compounds that contain the ions that we need in our body. So to write a good formula for an ionic compound, we have got to make sure the compound is neutral. Compounds are always neutral, right? Now, how do we make it neutral? Well, we have to make sure that the charges of the cations and the charges of the anions add up to the same number. So there's the same number of positive charges as there's the same number of negative charges. Let's say I've got a cation with a +2 charge and an anion with a -2 charge. Then a 1-to-1 ratio would make it neutral. You have as many positive charges as you have negative charges. Okay? So let's just do some examples with this. Calcium, if it has a +2 charge as an ion and fluorine as a -1 charge, if I want it to be neutral, I have to have as many positives as I have negatives. Well, if I double up on how many of these I have, if I had 2 of them, I would have 2 minus charges to go with it. Well, how do I write a good formula that shows that I have 2 of those? I write it as CaF2. Now, look here closely. Did I write any charges? Whoops. Or charges written in when I write the formula? No, you don't write the charges there. They exist. Calcium has still got that +2 charge. The fluorine still has the -1 charge, and I have 2 of them. But when you write a formula, do not write it as Ca2 plus F2 with a minus up there. Don't do that. Let's put an X through that. Okay? All right, let's try another one. Fe, 3 plus with a Cl minus. Well, again, I need as many negative charges as I have positive charges, so I would have to have 3 of the chlorides in order to balance out the positive 3 of the irons. Okay, so FeCl3. Now, let's look at some things that kind of start playing out here as we look at that. Notice that the charge, and I want to erase this out of the way here for just a minute. When it says it's minus, what does that mean? Minus how many? It's a -1, right? We just don't write the 1. We're really lazy and we don't want to write 1s in if we can avoid it. So we just write F minus. It has a -1. Now whatever the charge is up here becomes the subscript there, and whatever the charge is up here becomes the subscript there. That's kind of a quick and dirty way of coming up with a formula. It isn't always correct, okay? We'll see why that would not be correct, because when we write these formulas, we want them to always be empirical formulas, right? Ionic compounds are written as empirical formulas. You have to make sure it's the lowest possible whole numbers. So sometimes when you take it and you do the crisscross, which I'm going to crisscross it down, sometimes when you do that you're going to end up with numbers that aren't the lowest possible whole numbers, in which case you've got to make sure you reduce it down to an empirical formula. Okay, let's have you try one. I've got 2 ions here, manganese with a +6 charge and oxygen with a -2 charge. I want you to stop the video and I want you to think about what a good empirical formula of that compound would be. Well, hopefully you chose A. I think if you were going to make a common mistake, you would have chosen B, okay? A lot of people might have chosen B, but B is not quite right. If you do the crisscross and you do whatever this is, so manganese, oops, that's not manganese, that's magnesium. Silly me. Manganese 2 and oxygen 6, that's the crisscrossing them down. You gotta always stop and say, is that the lowest possible whole number, subscripts? And you can reduce that down to MnO3. Now, I probably wouldn't have thought the crisscross. I would have said, okay, I've got 6 positive charges, I need 6 negative charges. Well, to get myself 6 negative charges, all I have to do is multiply by 3. So that tells me I need 3 oxygens for every manganese. All right, let's do this last one on our list here. We have the Mg with a 2+ charge and the phosphate. Okay, phosphate has a 3- charge. If we do the crisscross down, this charge becomes the subscript and this becomes the subscript. We have Mg3, PO4, and 2. Be careful you don't leave it that way. It looks like I have 42 oxygens. When there's a polyatomic ion, and when there's more than one of them, you have to put parentheses around it. Let me say those 2 criteria. Okay? When there is a polyatomic ion, and when you have more than one, you use parentheses around it. Okay? If it were, let's do one more. Let's do barium and let's do sulfate and write a good formula for that. Well, they both have a 2 charge, which just needs to be a 1-to-1 ratio. This would be BaSO4, and there's only one of the sulfates, so it is not correct to put the parentheses around there. You have to have a polyatomic ion, you have to have more than one of them, and then you would use that. And if you just use the crisscross method, you would have come up with this. Would that have been correct? No. So I wouldn't go to that crisscross method if I didn't have to, crisscrossing them down. But sometimes when you've got something especially like this where you can't just mess with one to get the charge of the other, sometimes that crisscross is easiest. But let's think about this one without crisscrossing. With 2 and with 3, what we're really doing is coming up with the lowest common multiple between 2 and 3. What's the lowest common multiple of 2 and 3? Well, it's 6. So how many magnesiums would I need to get 6 positive charges? You would need 3 of them. And how many phosphates would I need to get 6 negative charges? I would need 2 of them. So its common multiple, least common multiple, is really what you're doing here as you're coming up with formulas. When there isn't a nice, if I just double this one, it helps me get the charge of the other, or if I just triple this one, it helps me get the charge. When you have to do something to both of them, you're coming up with the least common multiple, and that's when it's kind of handy to take the, oops, sorry, get it back. Just don't know which way to go. That's when it's kind of handy to take the power of the one to make the subscript of the other, and not necessarily think about what's really behind all that, which is the least common multiple. Okay, so now you can write a formula for ionic compounds if you know the charges of the ions. What we have to do next is we have to, if we're given a formula, come up with a good name for that compound. So you know its formula, now we need to know its name. And you're not allowed to, see, I had a student, my first year teaching, he would see something like this, and he'd call it feckle, okay? He said, I need some of that feckle. We'd be in lab because he'd just kind of make up a word, come up with those. Can't do that. It's got to be a special way of naming it. So we're going to go through the rules, and then we're going to practice those rules. And the ionic compound rules are very systematic, and there can only be one name for each compound. Can't be ambiguous at all. So here's the rules. First of all, you can't do it unless you know the names of the ions and their charges. So you have to have memorized those polyatomic ones. But let's say it's not part of a polyatomic ion. Let's just say it's a metal cation. Metals, keep the name of the metal. That's the easiest one. So sodium as a metal is sodium. Sodium as an ion is sodium. Now we might tack the word ion in there, it's sodium ion. But if it's within a compound like sodium chloride, Na, in that compound NaCl, it's just called sodium, okay? Don't have to do anything fancy to it, okay? The second rule deals with naming the anions. If it's a nonmetal, it becomes an anion. We're not talking our polyatomic ions where we've memorized names. If it's an anion and now it's an anion made, sorry, if it's a nonmetal that has become an anion, then what you do is give it an IDE ending. If you look back at our list of polyatomic ions, some of those polyatomic ions also have an IDE ending. So those were memorized. But any of the nonmetals, look at a periodic table. Okay, get one out, look at it. Nonmetals in the top right-hand corner, right? Any of those nonmetals, if they become an ion, will get an IDE ending. So let's look at some examples of that. Let's just think of an example of that first of all. Let's say we have the nonmetal chlorine, okay? There is the element, it's chlorine. Cl minus is an anion that contains a chlorine. So that would be called, this is chlorine, this is chloride. So it gets an IDE ending. Drop the old ending, give it an IDE ending. Okay, so we can name our ions. Now we're ready to name our ionic compounds. You always name the cation first and then the anion. Okay, cation, then anion. Easy enough, and it's a two-word name. So that is why sodium chloride, we name the Na, it's sodium, the Cl, chlorine, but no, let's give it an IDE ending, sodium chloride. Okay? Magnesium fluoride. The formula is MgF2. The name, I name magnesium as magnesium. Fluorine gets an IDE ending and it's fluoride. Now, look at this note. We do not, in anywhere in the name, do anything to state that there were two of those fluorines. It is just understood if somebody knows anything about a periodic table, and I'll teach you all that stuff as we go. Actually, you've seen it, I think, already. But magnesium has a +2 charge, fluoride has a -1 charge, so the formula has to be MgF2, and we don't tell them that in the name. All right, here's one that contains a bunch of two different polyatomic ions. We have ammonium is the name of the cation. Yes, there's two of them, but we don't tell a person that there's two of them. They have to figure it out on their own. Chromate is the name of this polyatomic ion. Chromate happens to have a 2- charge, and ammonium has a +1 charge, so that would be why it's got 2 ammoniums for every chromate. But we just name the cation first, then the anion second, 2 words, and it's not like a proper name. We don't capitalize it, okay? It's just, they don't get capitalizations for them. Okay, that's rule number 1. Rule number 2. There are some metals, certain metals, and it's usually in the transition metal area, that can have more than one cation, meaning more than one charge for that metal. Okay? And when that is the case, we would have to tell a person when they're reading the word, reading the name, what the charge is on that metal. If you look at a periodic table and find iron, for example, you can't look at the periodic table and know the charge of iron. There are 2 common charges of iron. There's Fe2+ and there's Fe3+. Those 2 common. You cannot look at a name that was just iron chloride and know which charge it is. You can't go to the periodic table and say, oh, there's iron, therefore I know its charge is, and there it is. You have to be told what its charge is with the name, and the way you're told is the charge, and that's in red. Students want to have it think that it means a lot of different things. It only means one thing, and that is the charge on the metal. And you use a Roman numeral to designate its charge, okay? So when I see FeCl2 and I wanted to name it, I would have to call it iron 2 chloride. Now, how in the world do I know it has a +2 charge? And that's what the Roman numeral 2 is. Well, I know by looking at the periodic table that chloride has a -1 charge. And there's 2 of those chlorides, okay? So I have 2 -1s. If I have 2 -1s, then I have to have a +2 on the iron if this thing is to be neutral. And we know that compounds are neutral. So I know that iron has to be a +2 charge. And so when I name it, it's going to be iron 2 chloride. All right, here is MnO. MnO. Now I'm telling you right now that it's manganese 2 oxide. Now how do I know it has a Roman numeral 2 after it? Well, oxygen, when I go to the periodic table and find oxygen on the periodic table, I know that oxygen is going to have, as an ion, a 2- charge. And it's a 1-to-1. There's 1 manganese for every oxygen. So manganese better be a 2+ charge to go with it, because the whole compound has to be neutral. As soon as I know that, I know it's manganese 2 oxide. Now I have a little bit of a typo in here, and it's not something that you're going to get counted wrong if you accidentally do. But the fact of the matter is there's really not supposed to be a space between the word and its charge. It just runs right to it, because there's just supposed to be 2 words. The first word, iron 2, and the second one, chloride, and that 1 space in between those 2. Now, what do students want to believe that the Roman numeral tells them? Because they'll see lots of examples. So often the charge becomes the subscript, right? So often the charge becomes the subscript and we crisscross it. Let's see if I can make it work here. We crisscross it down. It's not going to write. When that happens, we see a 2 for the chlorine, and so a lot of people are going to start thinking that that Roman numeral 2 tells you how many chlorides there are. Or if you saw 2 chlorides, that must be the Roman numeral you're supposed to have. But that's not what it tells you. It is telling you only the charge on the metal. Okay, a couple more things to note. The only way to determine that Roman numeral, okay, and there's our Roman numeral. The only way to tell us that Roman numeral is to know the charge on the nonmetal or the charge on the anion, and then calculate the charge on the metal. That's what the Roman numeral is, okay? So the second point there is, how do you determine that charge? Look at the charge of what it's connected to. You'll always be able to know what the charge of the anion is. And once you know the charge of the anion, you'll be able to calculate the charge on the metal, and that will give you the answer to that. So now we kind of have a schematic up there, what we're going to do. We're going to name the metal, or it might be a polyatomic ion, cation. If the metal needs a charge, we'll put that in Roman numerals and parentheses after it. And then we will name the non-metal anion or polyatomic anion after that. So what you have to be able to do is go in both directions. So if you were given the formula, you have to determine the name. If you're given the name, you have to determine the formula. You need to be going in both directions and correctly using your rules as we go. So we'll practice going in both directions. Okay, here's a few examples. I've got about told you what the name of it, because when I see a formula, I want to just name it. Okay, BaNO3, 2. We have 2 of those NO3s. So we have to go in here and recognize that we've got a cation, barium, all right? And then we have our anion, and we name it. It's nitrate. And we have to stop and think, do I need a Roman numeral? Now, I want you to pull out a periodic table. If you don't have one in front of you, stop and go get you one and come back. So you look at that periodic table and you locate barium. When we see barium in that 2A family, okay, it's an alkaline earth metal, they always, if they're in a compound, now not if they're just the metal, but if they're in a compound, if they're in an ionic compound, they will always have a 2+ charge. And if that isn't always, we do not need a Roman numeral. So we don't put a Roman numeral with barium nitrate. And remember, there's nothing that we write that tells us that there's 2 nitrates. A person has to figure that out from the charges. Okay, so let's go to the second one. The metal is nickel. So we write that. The nonmetal, it's an oxygen nonmetal, but it's a ion, so it gets an IDE ending, so it's oxide. Now I've left room for a Roman numeral if I need one. Now as I go to the periodic table, let's talk about the ones that don't need it. The 1A metals are always +1 in a compound. The 2A metals are always +2. They don't need it. So we go into that middle zone. Most of them do need them, but there are a few that don't. I want to write the ones that do not need a Roman numeral, okay? Silver, shoot, I've done it again. Let's get you back up here. Okay, who does not need a Roman numeral? Silver, cadmium, zinc are the transition metals that don't need a Roman numeral, because silver in a compound is always going to be +1. Cadmium is always going to be +2. Zinc is always going to be a +2. And there's one other that's right next to zinc. Aluminum doesn't need a Roman numeral. Okay, now it's not a transition metal, is it? It's not a transition metal, but it doesn't need a Roman numeral. Underneath aluminum, there's a lot of other metals, and those metals like lead or gallium or tin, you actually do need to use those Roman numerals for those guys. So if it's not a 1A metal or a 2A metal, or it's not one of these 3 metals in the middle there, then it needs a Roman numeral. So does nickel need a Roman numeral? Yes, it does. So let's figure out its Roman numeral. The way you figure out its Roman numeral is with what's connected to it. So we go to the periodic table and say, hey, there's oxygen. What's the charge on oxygen as an ion? And based upon its location, we know it's 2-. So if it's 2-, then the metal has to be 2+. But we don't put a Roman numeral 2, because what we want to know is the charge on each nickel, not the charge on the whole group of nickels. If there's 2 nickels and combined they have a +2 charge, then we have to know that this is going to be a Roman numeral 1. Each nickel has a +1 charge. There's 2 of them, so it's a +2 charge to balance it out. So this would be called nickel 1 oxide. That's how we would say that. All right? So you have to go in both directions. Now I'm giving you the name and you have to come up with a formula. Now students, hear me say this. Write the charges first before you ever try to write the formula, okay? There should be this middle step when you're given the name of an ionic compound. You stop, you come up with the charges first, and then you figure out subscripts after you do that. So let's do that step here on the screen. Calcium, we go to the periodic table. We see that the calcium is in the 2A family, so we know that calcium has a 2+ charge. Then we have phosphate. Phosphate is not on the periodic table. It's not P, it has an ATE ending, is a polyatomic ion, and we have to memorize that phosphate is PO4 with a 3- charge. You have to think those steps first. Now we're ready to come up with a formula that gives me as many positive charges as negative charges. If there's calcium with a 2+ charge and phosphate with a 3- charge, then we're going to need 3 of these to give me a +6 and 2 of these to give me a -6. Think about the crisscross down method, that kind of works there. Okay, so that is calcium phosphate's formula. Nickel sulfide. Well, nickel is Ni. Because they gave me a Roman numeral 2, I don't have to go to the periodic table. They're telling me the charge. It's nickel with a 2+ charge. Sulfide, that's sulfur with an IDE ending. That means it's the element sulfur, but as an anion, give it a charge. Look at the periodic table. What charge would sulfur have? It's a 2- charge. Okay, so I have a nickel with a 2+ charge and a sulfur with a 2- charge, so it's going to just be NiS because a +2 and a -2 will work together there to give me a nice neutral formula with the lowest possible whole numbers. So we've practiced going in both directions. If giving a cation, given the names, we can get the formula, and if given the formula, we can get the names. When you do the second one where you're trying to get the formula, my key to you is to make sure you do this step first before you do this step. So many people look at a name like nickel sulfide and just put the Ni and the S. In this case, it's correct. But you don't know it's correct until you've written those charges down. So the student who is going to make a mess of calcium phosphate will just say Ca for calcium, PO4 for phosphate, and think it's CaPO4. It's not. You've got to use those charges. All right, you look at this one, stop, and see if you got the right answer for this one. Well, if you picked A, you'd be correct. A, it's silver oxide. Cation is silver, anion is oxide. You don't give it a Roman numeral 2 because that's, first of all, that's not the charge on the silver. Each silver is +1. But silver was one of those elements where I told you its charge is always +1, so you don't tell somebody its charge. So silver oxide is the correct answer. Okay, here's another one. TiS2, you're going to name that one. Stop, think about it, pick your answer. Okay, did you give it a Roman numeral? If so, you're off onto the right start. Did you give it the correct Roman numeral? It should be titanium 4 sulfide. Now, what would be the common mistake? Common mistake using a Roman numeral 2, because you think, oh, well, there's a 2 here, I'll crisscross them back up, and therefore those are the charges. You cannot go back up with those, because once you have the subscript that's the lowest possible whole numbers, we don't know that those are the charges. You can't take them back up. Do not do that. Common mistake. Don't want you making those common mistakes. So how would you know it's 4? You go to the periodic table. The periodic table tells me that sulfur is going to have a -2 charge. And there are 2 of those sulfurs. 2 sulfurs. So what total negative charge do I have? You put those together and it's -4. So titanium has to be +4, and that is a Roman numeral 4. So that is why it's titanium 4 sulfide for this one. Okay, so now we can write a formula given a name. We can give a name if we have a formula. We can go in both directions. We can write good formulas that are balanced for ionic compounds, always remembering that it's the lowest possible whole number subscripts that we will use when we're writing a good formula for an ionic compound. Next, in your next video that you'll watch, we're going to learn the rules for naming molecular compounds.